Okay, good afternoon. Today I'll be talking about the Schwarz alternating method for multi-scale coupling in contact and solid mechanics. And this is joint work with Alejandro Mota and Jonathan Hoy from Sandia National Labs and the University of Southern California, respectively. So let me start with a little bit of motivation. A lot of the problems that Sandia National Labs is interested in involve large-scale structural failure. Large-scale structural failure frequently originates from small-scale phenomenon like defects or microcracks, which grow quickly in an unstable manner and can lead to the large-scale structural failure. So this drew failure of a Boeing 737 aircraft due to fatigue cracks is one example. And what we found is that to be able to capture these sorts of phenomena, we really need concurrent multi-scale methods in doing these simulations. And additionally, we need stable, accurate, and robust methods for simulating mechanical contact, which inevitably initiates in these kinds of scenarios. And so examples of contact would be touching surfaces, sliding, tighten bolts, impact, and so on. And so, while methods for simulating the bulk behavior in these mechanical type simulations are fairly well established, existing methods for contact enforcement, such as the penalty, the Lagrange multiplier, and the augmented Lagrangian methods, often suffer from poor performance in the form of long simulation times, loss of accuracy, lack of robustness, and so on. And so in this talk, I will be presenting a new approach for simulating multi-scale mechanical contact that's based on an approach known as the Schwarz alternating method. And so I'll kind of overview this approach on the next slide before getting into the details of how we use this approach for enabling contact. So the Schwarz alternating method is summarized here. It's probably the oldest domain decomposition method out there, proposed in 1870 by Hermann Schwarz for solving the Laplace equation on irregular domains. And it's based on a very simple idea that if you want to solve a problem on a complex domain, you can decompose that domain into simpler subdomains and then use solutions on those simpler subdomains to iteratively build a solution on the more complex domain. And so I have illustrated here the method in the context of the simple coupling involving circle and a square. So let's say you want to solve a problem on this domain that's the union of the circle and the square. You start by solving the problem on the circle omega-1. You use whatever boundary conditions are prescribed on the outer boundary. You can use an arbitrary initial guess to get this started on gamma-1. You then go to omega-2, you repeat the process, but now instead of using arbitrary boundary conditions on gamma-2, you can take the solution you obtain in omega-1, interpolate it onto gamma-2, and use that to define the boundary condition. And then you go back to omega-1 and you repeat. So information kind of propagates through these transmission or boundary conditions that you impose. Now you'll notice I have an overlapping and a non-overlapping domain shown here, and it turns out that depending on which of these cases you have, you need different kinds of transmission conditions. For the overlapping case, Dirichlet conditions will give you a convergent solution, as shown by several authors cited here. For the non-overlapping case, you need either Robin or alternating Neumann-Dirichlet conditions to get a convergent method. So, where the Schwarz method is commonly used is in the linear solver literature, where it's used as a preconditioner for Krylov iterative methods for solving linear equations. What we're proposing here is not to use it as a preconditioner, but rather to use the method as a solver, as a discretization method for fully coupled nonlinear PDEs. Okay, and so we've done some work the past few years in developing the method as a discretization method for multi-scale coupling in solid mechanics. The details are in these two papers that are listed here at the bottom. The formulation here was overlapping, and the method we developed has a number of desirable properties. It enables concurrent coupling or two-way coupling. It's free from non-physical artifacts that are prevalent in other multi-scale coupling methods, has a theoretical convergence guarantee. It allows you to couple different meshes, different element types, different solvers on different time integrated, different time steps in a sort of plug and play framework that we've developed. It's easy to implement in existing HPC codes like our Albany and Sierra codes, and it's scalable, fast, and robust in a variety of problems that we've applied the method to. So what we're doing in this work is essentially kind of taking this earlier work for the multi-scale coupling and extending this to enable multi-scale contact simulations. And I'll go through kind of the main steps of this formulation, which is now a non-overlapping Schwarz formulation. And the key idea that's kind of underlying the development of this method is that if you have a contact problem, you can remark that this contact problem can be viewed as a coupled problem while your two or more bodies that are involved in that contact are in contact. So the way that the formulation proceeds is as follows. Before contact, your simulation goes as usual. Here we have this circle and square, and they're approaching each other and towards an impact that will occur. The next step here is detection of contact. So just like in a regular contact algorithm, you need a proximity search. You also need to apply some contact conditions to determine when contact has happened. And the contact conditions that we formulated are listed here. First, we have the overlap condition, which is triggered when two or more objects or domains have begun to overlap or penetrate each other, like shown here. And then the second condition is what we call the push condition. And this is triggered when you have tractions at the interface in the compressive regime, and also when you have contact having occurred in the previous time step within the Schwarz algorithm. And so the last step is the enforcement of contact. And so basically, once you have this overlapping situation, which you don't want because you have interpenetration, you need to correct this. And so for this, we apply this alternating Schwarz iteration that I described earlier. We apply Dirichlet-Neumann transmission conditions because our goal is to get into this non-overlapping framework where in subsequent iterations, you either apply a displacement condition or a traction condition in an alternating manner. And what I wanted to call to your attention is that in this method, there are no contact constraints that you see in traditional methods, like say the penalty method. These contact constraints are replaced with boundary conditions applied iteratively at the contact boundaries. So in the interest of time, I'll just kind of show some examples, or one example rather, a 1D impact problem where we've verified and evaluated the method. This problem involves 1D identical linear elastic prismatic rods shown here that impact each other. This problem has an exact analytic solution that's detailed in this Carpenter reference. And in addition to the Schwarz alternating method, we evaluate three conventional contact algorithms: the implicit and the explicit penalty method, and then the forward increment explicit Lagrange multiplier method. And for all these methods, we use a Newmark beta time stepper. For the Schwarz method, we try different couplings. We do explicit, explicit, implicit, explicit, and implicit, implicit to illustrate the ability of the method to couple different time integration schemes. And for the implicit, explicit coupling, we also use different time steps in different domains to illustrate that capability. So some of the kind of main results are shown in the next few slides. This is showing the contact point position of the rightmost node of the left bar as a function of time for the 6 different methods. You can observe that the penalty methods in this blue and yellow, they overpredict the contact point location between the impact and the release time. The explicit Lagrange multiplier method does better, but it severely underpredicts the release time itself. In contrast, the Schwarz methods give you a very accurate solution, and they capture the release time to an accuracy of about 0.1%. Similar results are shown for the mass average velocity, where the Schwarz variants calculate this quantity to a sufficiently greater accuracy than any of the conventional methods, especially near the release time, where you see a lot of error in the conventional methods. And where the Schwarz method really shines is looking at energy conservation. So total energy should be conserved for this problem. You can see that the conventional methods exhibit energy loss of up to 9% following contact, whereas we get at most a 0.25% error in the total energy for the Schwarz methods. Unfortunately, it turns out that this method, the Schwarz method's ability to conserve energy so well is actually has some negative consequences. And you can see that by looking at the contact point force. This is shown for the conventional methods on the left and for the Schwarz methods on the right. And for the conventional methods, while you see some undesirable artifacts like this overshoot and some oscillations, in general, you get a pretty smooth contact force solution, right? That's not true for the Schwarz methods. You can see a lot of oscillations here, and these oscillations are actually showing that we have what's called a chatter problem, where you have the loss and subsequent reestablishment of contact happening during the simulation. And interestingly, this is actually related to the method's ability to conserve energy, as shown by Solberg et al. In 1998. You really need some energy dissipation to avoid this chatter problem. And so since our methods are so good at conserving energy, we see this, and in fact, you can show that the methods with the largest total energy loss on the previous slide have the least amount of chatter in this result. And so just to kind of wrap this up, one of the things we're looking at right now is to deal with this chatter issue through the introduction of dissipation or numerical relaxation into the method. But overall, we've had really promising results on this 1D problem. Future work is also going to look at evaluating the method in the case of multi-D, where you're going to have a little bit more development that needs to happen there, and implementational details will need to be worked out, including how to develop operators to consistently transfer contact traction boundary conditions in that Schwarz condition that we have. So I'll end here. Thank you for your attention. Happy to take questions.